This session is to give you some brief about the data sheets of the devices that we are using for assignment number one. So the microcontroller that you need to use in this assignment is at Mega 16. So it has all the features, you can read them. And this is the pin out of this at Mega 16. So it is 40 pin PDIP, which is true hole type. So you can just easily put this on a breadboard. So these are the pins that is used to for ISP programming. If you have this these pins, just goes to the in series programmer ISP. So I have uploaded a video regarding how to program a microcontroller using USB ASP. So if you use this USB ASP, the programmer, so it's like some kind of USB type programmer comes like this. So it has a 10-pin connector. So you have to correctly connect these right pins to this USB ASP to these pins, and then use Atmel Studio to program your microcontroller once you have a hex file. So, but in this assignment, it is all is based on simulation, so you don't need to worry about this programming. So if you use Proteus, just double click on the microcontroller and then import the hex file and just set the frequency to 1 megahertz. Then it will be all set. And so, like, so you had in simulation in Proteus, you don't need to connect to BCC and ground, but if you wish, you can connect it to a 5-volt supply from the LDO output and to the ground of the LDO. And so AVCC should also connect it here, and the ground should comes to here. And you can add a capacitor here, like a 0.1 microfarad for noise immunity. If you're using the internal 2.56 voltage reference, and so it is all. So these are the ADC channels that you can use for any analog signal, and so these two are these interrupt pins that you can use for interrupt services for external interrupts. And any of these digital pins port B, port T, port C, you can use to interface your LCD and some LED lights or switches. Any digital inputs and outputs, you can use these digital pins, and you can use this port for any ADC analog signals. This is for analog signals. And finally, for PWM, just read this the datasheet timer 2. So you have to go to the if you wish to, you can refer the lecture notes as well. So the timers and counters go. If you go to this section, you can get some idea about the this phase correct PWM scheme. This is the phase correct PWM, and there is a corresponding pin to generate this from the microcontroller. Read this one, then you will figure it out which pin that you need to use for your motor driver. So if you look at this, somewhere you can see which pin you can use for generating that frequency. So that pin should be connected to the your motor drive, right? So one of these pins in your microcontroller is for generating this PWM, So you have to use that pin to your L298 motor driver, so which is generating a PWM signal. So that's all about this microcontroller. So you are using internal 1 megahertz oscillator, and now I will explain about this temperature sensor. This is the temperature sensor that you are using. So that is LM35 precision centigrade temperature sensor. So all you need to do is provide plus 5 volts, positive 5 volt here and ground here, and you can take the analog signal from here. So it is like a linear range, which means here you have the temperature and here you have this voltage. So for example, now at 0 Celsius, you should get a 0 millivolts, and if it is 25 Celsius, you will get here you can see this range. Range is in right. This is the range. 10 millivolts per centigrade, which means if you have 25 centigrades, which should be multiplied by 10 millivolts, which means like the corresponding voltage is 250 millivolts. Okay, so this is in millivolts and this is 250. Likewise, if you have 100 degrees, you will get 1000 millivolts voltage or 1 volt voltage, right? So that signal goes to the microcontroller analog channel. So using ADC, you can convert this voltage to a ADC value, and then you can back calculate the corresponding using an equation corresponding temperature, right? So that's all about this temperature. So it has plus, minus, and the output. So then we are moving to the LDO regulator that is used to convert this battery voltage to 5 volt. So basically, it has different configurations. So in simulation, we can use this version. It is very much simple. All you need to do is just provide the 6 volt to the input pin, and it has a ground pin, and enable shutdown. Typically, you have to you can connect it to directly to the 6 volt supply, which means you provide a logical high 6 volt, then this chip is enabled. If you set it to 0, the output will be disabled, but we are using the output voltage all the time. We can just directly connect this enable pin to the input pin 6 volt, and there's a bypass pin. So you can connect a 460 picofarad capacitor to that pin, and from the output pin, you can get the 5 volt output, and use 2.2 microfarad capacitor out at the output for stability purposes. This is how you just connect. If you use the Proteus, just prepare this data sheet, and V in and enable should goes to 6 volt, and output goes from the 5 volt output. Bypass, you can either keep left it floating, or you can just connect a capacitor. Then you can convert the 6 volt to stable 5 volt supply, which can be used for your microcontroller and other sensors. And this is the motor driver. So this motor driver IC looks like this. It is a dual motor driver. Most of the time you can, here using Arduino and robotics, you have seen this one. There's a motor driver board for that, but internally this is the chip that is used. You can control 2 motors, but here we are just using one channel, which means we are connecting one single channel. This is the motor. You can use another motor here. This is helpful when you using robotics or any other things, if you have wheels in your motor driver. But you can use this one for the moment. Now you have to provide 6 volt to here, right? And the pin number 1 sense goes to ground. You don't need this sensor resistor. You can just directly connect it to the ground. This is 6 source and ground. This is how you power up the chip, providing voltage supply. And all these are the control signals. These are the control signals. These are the control signals, and this is the power. So power and control pins are separated. Now the thing is how to get this done, right? Now first thing is you have to set this enable high, then only this edge bridge is activated. So this should be logically high. So you can just connect this enable pin to the microcontroller MCU and set it always 5 volt, right? So then this motor, this bridge will be activated. Okay. So if you want to rotate the motor in one direction, assume like in this way, but it is not. Since this is a DC motor, you can, by changing the polarity, you can rotate in any way. Right. So if you assume like we want to rotate the motor in this direction, so you can set this I in 1 to 1 and this one to 0. Okay. While keeping this one at logic 5. I will assume like all these logic signals are 1s and 0, like logically 5 volt means logic 1, 0 volt is logic 0. Okay. So we will set this enable to logic 1. So this bridge is activated. And if I set I in 1 to 1 and this to 0, you can see this AND gate is, this is 1 and enable this 1. So this all are true. This will be 1, output will be 1, right? So this transistor is activated, turned on. And same time, since this is 1 and there's a NOT gate and this will be 0, and this is enable 1 and this is 1, and therefore you can see this AND gate and 0 and 1 and is 0. So this transistor is turned off. And this side you can see this enable is 1, so this is 1, and this is connected to the IN2, which is 0. So this transistor is turned off. And now this is 0 and NOT of that is 1 and enable is 1 and this is 1. So this transistor is turned off, which means that you can see the power is coming from this VSS, comes to this transistor and coming through this transistor and goes to the motor and goes from through the motor and coming back. And this transistor is turned on, and through this one it goes to the ground, right? That is how this the power is the current from the battery is going through this transistor and go to the motor and comes from here and goes to down. So if you change the logic, now example, if you set this to 0 and this to 1, these two transistors will be activated and the power current will flow from this transistor through the motor in this way and returning back through this transistor to the ground. So in the earlier case, we had the current flowing through the motor in this way. And if you change the logic to 0, 1, the current will be flown in the other way. So the direction is changed. But in this example, it is not, we don't need to change the direction. In that case, we can use, keep these settings always here. So these pins should go to your microcontroller at Mega 16. By changing this logic, you can enable the motor running, right? But this is always true. This could be like a always 5-volt signal, and this is logic 0, and this is the PWM signal. So which is something like a pulse width modulated signal. By changing this duty ratio, like this time cap, you can control this speed. I mean, if you set this one to very small scale, something like this, the average voltage of this PWM signal will be very low. And if you use the high PWM, like something like this, the average voltage will be somewhere here, right? So which means the motor will drive with like a very large current. So its motor is speeding up. So the lowest voltage you can have in the PWM 0 volt, and the maximum voltage you can achieve is 5 volt. In between, you can, by changing this time period, you can adjust this DC voltage from 0 to 5, right? So if you want the maximum speed, you can change the PWM duty cycles to 100%. So it is typically 5 volt, and the motor will driven at the highest speed. And if you want to run in the lowest speed, like 0 RPM, you can set the PWM duty ratios to 0. So it is the motor will be turned off. In between, by adjusting this duty ratio, you can achieve any speed that is required. That is what we call PWM. So the speed and direction can be adjusted by using this one. If you have another motor, you can connect it here and driven from another channel of the microcontroller. But this application, you can just use out 1 and out 2. And make sure this pin of the microcontroller at Mega 16L goes to the PWM phase correct PWM output channel, which goes to IN1. And this one, IN2, can be go to any digital pin. And this one can be go to any digital pin. So then you can change the speed of the motor by adjusting the PWM duty ratio. Okay, so that's all about the datasheets and explanation regarding this assignment. You can read them carefully to get more understanding, and you can watch some YouTube videos in the internet to refer more about this, how this H bridge works. But this is a very simple basic explanation. So this is how you this is a true hole version. They can have this SMD version as well. So when you building your PCB, make sure you follow this PCB layout guidelines. So that will help you to build your PCB in a safe manner. This one, they haven't shown very clear picture, but there are some other ICs I have seen. They have a recommended layout. For this one also, this LDO, let's see whether we have a recommended layout. Yeah, so in this LDO regulator, so this is a recommended layout. It's a plain no, they don't have a recommended layout, unfortunately, but we have to use the standard. This is pretty much the ground plane. If you're using this package, there are different packages comes with this one. This is one package and this is another package, and like that. Depending on the package, you have to decide by yourself. Right, so that is all about the data sheets, and so you can refer these data sheets uploaded to LMS and read them carefully before you do your assignment. Right, this is the end of this session.